Welcome! In this lecture, you are going to learn basic facts about the working of heat exchangers. Heat exchangers are used everywhere. They are basic and essential components of all energy supply and distribution systems. They are used to transfer heat from one medium and one place to another, with the purpose of either heating or cooling. For example, a gas boiler is equipped inside with a heat exchanger that brings the heat obtained by gas burning to the radiator pipes. The radiator itself is a heat exchanger too. In industrial plants and electricity plants, heat exchangers are used a lot. For example, to cool down cylinders or hot fumes and steam by bringing them in contact with cooling water from a river, for instance. A water source heat pump may use a heat exchanger like the one on the picture left to tap heat from a river or the sea. There are many different designs, but we will explain the working on a simple one, just a pipe. To make heat exchange possible, two parameters are very important. The first one is that there should be a temperature difference between the two media that are going to exchange heat. Let's take a simple pipe with water circulating in it and placed in outdoor air, something like your garden hose. The water that comes in is at 10 degrees Celsius. If the surrounding air is at 10 degrees too, and there is no solar radiation, you know intuitively that the water in the pipe will also go out at 10 degrees. Only if the air is much warmer, let's say 30 degrees, then the water in the pipe can absorb some heat from the outdoor and will go out at a higher temperature, 20 degrees in my example. So we need a temperature difference. Second, you need enough heat exchanging surface. If you have just a very short pipe or a pipe with a very small diameter, you also intuitively feel that there will be less heat exchanged and the water temperature at the outlet will be lower, in this example 15 degrees Celsius instead of 20. So, we have two important parameters, the temperature difference between the two media and the surface area of the heat exchanger. To calculate how much heat is needed to heat the fluid circulating in the pipe from T in to T out, we can use a simple equation. Q is ρ times C times T out minus T in. Always make a rapid check of the signs. If T out is larger than T in, the fluid has gained heat and Q is positive. If T out is lower than T in, the fluid has lost heat and Q is negative. ρ is the specific mass of the fluid in kilogram per cubic meter and C is the specific heat of the fluid in joule per kilogram Kelvin, and VR is the volume flow rate of the fluid in cubic meter per second. ρ and C are properties of the fluid circulating in the pipe. For instance, for water, ρ equals 1 kilogram per cubic meter and C is 4.18 kilojoule per kilogram Kelvin. According to the first law of thermodynamics, this energy Q must come from somewhere. In our case, it comes from the ambient air temperature. We have just learned that the larger the temperature difference, the more heat is exchanged. So, at the start of the pipe, the heat transfer is large, while at the end, the heat transferred is much lower because T out is close to T ambient. In general, we will consider an average temperature of the fluid in the pipe, T min. Please observe that this T min is not the arithmetic average and is therefore not in the middle of the pipe, but a bit more at the cold side. This is to compensate for the larger heat exchange at the start of the pipe. So, we will write that Q is H times A times T ambient minus T min, and it can be derived that this T ambient minus T min is equal to LMTD, the log mean temperature difference, defined as given in the equation below. If you know the temperature levels T out and T in and the quantity of heat to be exchanged, you can then relatively easily estimate the needed heat exchanger area by using the law of conservation of energy, by which the results of equation 1 should be equal to the results of equation 2, leading to the formula below. The surface area A determines the size of the heat exchanger and therefore its costs. Let's look a little bit more at what happens in the heat exchanger pipe. We are looking at heat exchangers immersed in a heat source of constant temperature T ambient. Think for instance of outdoor air or a river, a lake or the ground. A furnace maintained at constant temperature can also be considered as such a reservoir. You see on the left a cooling application and on the right a heating application. Such reservoirs are used a lot to cool down hot water, steam or fumes from industrial processes and electricity plants, see the left figure. They are also used as a heat source, see the right picture, for instance for ground source heat pumps, or to make warm hot tap water from the furnace of a boiler. In the case of a cooling application, look at the left side. The hot fluid circulating from left to right in the pipe immersed in the cold reservoir cools down, releasing its heat Q to the reservoir. Heat goes always from warm to cold, as you know. You see here the corresponding temperature levels. The reservoir has the lowest temperature T ambient. At the beginning of the heat exchanger, the fluid is hot and at the end it is cold because it has given its heat Q to the reservoir. Maybe you expect the reservoir to become warmer, which would be the case if it was small, but we consider large reservoirs being replenished continuously. Think for example of the sea or a large lake or just outdoor air. Please pay attention to the fact that the temperature at the cold side of the pipe is always higher than the temperature of the reservoir. It cannot cross the light blue line. There is a temperature difference needed to exchange heat. In the case of a heating application, look at the right side of the slide. The cold fluid circulating now from right to left heats up, taking its heat Q from the reservoir. Heat goes always from warm to cold. You see here the corresponding temperature levels. The reservoir has the highest temperature. At the beginning of the heat exchanger, which is now at the other side on the right, the fluid is cold at T in and at the end it is warm because it has taken heat Q from the reservoir. Here too pay attention to the fact that the temperature at the warm side of the pipe is always lower than the temperature of the reservoir. Up to now, we have looked at heat exchangers immersed in a medium at constant temperature. But most of the time, the design is such that the heat transfer takes place between two fluids in movement in two different pipes. It may be water-water or air-air or air-water or refrigerant-water or refrigerant-air, etc. In short, there are two pipes being in thermal contact and exchanging heat together. Like here in parallel flow, also called co-current heat exchangers. The heat exchange is from the hot fluid to the cold one. The hot fluid is then cooled down while the cold fluid is heated up. There are other configurations possible, like this one, which is said to be in counterflow. The hot water comes now in at the other side of the heat exchanger, so TH in and TH out have been reversed, showing temperature profiles as below. Generally, counterflow heat exchangers are more efficient as the temperature difference between both flows is more constant. By the way, in these configurations, the log mean temperature difference must be calculated using this formula. Crossflow is also possible. You see here an air-water heat exchanger in which the air flows through plates perpendicular to a water pipe. There are many different designs of heat exchangers, all aimed at exchanging as much as possible heat with as small as possible heat exchanger and as low as possible costs. Heat exchangers are also used to evaporate or condensate fluids. Evaporation and condensation are both processes that take place at constant temperature. To evaporate a fluid, a lot of heat is needed, called the latent heat of evaporation, QL. During the whole evaporation process, the temperature of the fluid remains constant. When a fluid condensates, it releases a lot of heat, equal to the latent heat of evaporation, QL. During the whole condensation process, the temperature of the fluid remains constant. It happens quite often that a heat source cannot be used directly and that an additional heat exchanger is needed. For instance, in a ground source heat pump, you would like to have the refrigerant circulating in the evaporator of the heat pump to take directly its heat from the ground at 9 degrees Celsius, allowing evaporation at 2 degrees Celsius in this example. But this is not wise, because if the refrigerant is leaking, it would contaminate the soil. It is then much safer to add an intermediate heat exchanger using water or water glycol as fluid, for instance, like this. A closed heat exchanger water loop takes heat from the ground, allowing the water to be heated to 3 degrees, for example. This water gives its heat to the evaporator and is therefore cooled down and goes back to the ground at 1 degree. The temperature of the water in the intermediate heat exchanger is between 1 and 3 degrees, as we just said, which is much too low to allow evaporation at 2 degrees Celsius. So, the design of the heat pump, entailing the choice of the refrigerant and the temperature and pressure levels, will have to change. In the picture you see that now the evaporation takes place at minus 5 degrees. The conclusion of this is that the final source temperature is not 9 degrees Celsius, as it could have been with direct heat exchange, but only approximately 2 degrees Celsius, the average between 3 and 1. So in practice, because of all kinds of regulations and considerations, one must add intermediate heat exchangers, which has design consequences. In this short course about heat exchanger, you have learned that heat exchangers are devices that transport heat from one medium to the other and also from one place to the other. To allow for heat exchange, a temperature difference is needed between the two media as well as a surface area large enough. You also need to remember that heat always flows from warm to cold. We studied diverse heat exchanger configurations with their corresponding temperature profiles. This includes co-current, counter-current and cross-flow heat exchangers, as well as evaporators and condensers. And we also studied the temperature consequences of having to use intermediate heat exchangers for safety or legal reasons. So, I hope that you have enjoyed this course. Thank you for your attention.